Welcome back to ECE 442-542. We are getting into the fun part of the semester in terms of now we can design or we can play with controller design, try to design things. We started last time with this direct design of Ragazzini. The announcement is hopefully sometime soon I will give you homework number 5 and make that available, but it's due a week from tomorrow. So I hopefully will get that to you before a week from today. That's the plan. Keep thinking it's going to happen and then I'm interrupted. But today what I want to do is talk about the direct design of Ragazzini and go through a couple of examples. We'll start by summarizing the design steps, and that's not very many. There's only 2 steps in the design process, but some of those design steps take a little thought or a little design work. And so we'll talk about those. We'll develop some additional constraints. There will be 4 constraints or 4 restrictions in doing this design via Ragazzini, and those depend on what our plant looks like. And then we will go through the examples, and then we'll try to summarize and say, what did we learn by going through the design by Ragazzini approach that will then allow us to have more insight into subsequent design techniques. The plan is to talk about PIDs, PID controllers, proportional integral derivative controllers, after we talk about this. So we'll sort of reposition after we talk about the design by Ragazzini. PID controllers, if you're in the process industry, that might be 97% of the controllers that are out there, and there may be there are millions of controllers out there in the process industry, and most of them, 97%, are PID controllers. Meaning I don't want you to leave this class not knowing what a PID controller is and how you might work with one. So the first thing is you won't call it a PID. Okay, it will be a PID controller. Then we'll go into maybe some more classical transfer function designs. I haven't yet decided. It kind of depends on where we're going or how we feel. Maybe some root locus designs and state space-based designs. And then maybe system identification. We can just keep going and going. But that's where we're going. And somebody said, oh yeah, we just have a month left. So there's not a whole lot of school left, but half of your points are still available to you in this last piece of the semester. I'm not going to say the last half, but the last part of the semester. It's the second part after the break. Here's the design method of Ragazzini in a very quick description. First, the first step, so I'm saying there's 2 steps. The first step is to build or create a desired transfer function. And you know how to do that based on transient specs, steady state accuracy specs. Maybe we haven't talked too much about that, but a lot of times the more steady state accuracy you need, the more poles you need at the DC location, which is at z equal to 1. But we'll get there in other designs probably. They'll sort of take care of themselves in this design. Step 1 then is to build up that desired transfer function, T sub c, and that might have to be 5th order. But we know how to place 2 of those 5 poles as maybe our dominant poles, and the other 3, you know how to make those faster by making them closer to the origin. And you might make them completely fast and lock them right on z equals 0, maybe. Is one option. Once we have T sub c of z, then we showed where this formula comes from by really just solving the closed loop transfer function expression, T sub c of z, for the controller expression, c of z. Effectively what that says is, oh, you want to invert the plant, sort of cancel the dynamics of the plant, and then substitute in the dynamics that you need to make your closed loop transfer function look like the desired transfer function, T sub c of z. But what did we say last time that you better never do? Never, 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 never what? Cancel open loop poles that are unstable or open loop zeros that are unstable. Anything outside the unit circle, don't cancel it. If it's a pole or a zero, don't cancel it. And that's going to make some of these constraints in T sub C of Z. Just as a recall, there's what T sub C of Z is in terms of its parameterized form relative to the controller, C of Z, and the plant, G of Z. So we have to have already constructed this G of Z, and that might be from a zero-order hold of an analog plant, and you now know how to find that, how to find the zero-order hold equivalent. This is how the controller and the plant are connected, and that allowed us then to really just solve for C of Z from that relationship. We talked about the first restriction last time, but now we'll talk about more. But first, let's just remind ourselves what we talked about last time, which was restriction 1, R1. I'll label them R's because we already have C's all over the place, and C's for constraints. No, let's just say C's are our controller, C of Z. R's will be our restrictions. If our controller is a ratio of polynomials in Z, we need that to be causal. And I hope from last time you remember what that means. Quickly, what that means is your denominator degree needs to be greater than or equal to the numerator degree in order for your controller to be causal. And we went through this cross multiplication and showed how the output of the controller was related to the input of the controller, and we showed why, if you didn't have that condition, that you could have a non-causal relationship between your input of the controller and the output of the controller. So you need your denominator polynomial to be at least as big in order as the numerator in your controller. Here is our design formula. And if you look at this denominator in the rightmost piece, 1 minus T sub C of Z, no matter what T sub C of Z is, if you now combine it with 1, so if you now obtain a common denominator and take the numerator on this 1 to be the denominator that was in T sub C of Z, hopefully you can see that that expression is always going to be strictly proper, or the numerator will be equal in degree to the denominator in this 1 minus T sub C of Z expression. And if that's not making sense, go home, plug in a T sub C of Z, a hypothetical, and say, what's 1 minus T sub C of Z look like as an expression? And hopefully it will show or convince you that that's proper, meaning the numerator degree is the same as the denominator degree in this 1 minus T sub C of Z. So we're not changing the degree of C of Z by that denominator, meaning this is sort of not important in this next little bit of the discussion. But what is important? We have 1 over a ratio, so that now the plant zeros, open loop plant zeros, will end up in the denominator of C of Z, and the plant denominator factors will go upstairs and become numerator terms or factors. T sub C will just contain its numerator and denominator in that same relationship. But here's what we are trying to better understand. From the design formula, which is that expression, the pole zero excess in G of Z, so that's how many more poles you have than zeros in your plant to begin with, those will result in poles at infinity in your controller C of Z because of this sort of reversal of the factors when you're dividing by G of Z. Your zeros become poles and your poles become zeros because you're doing 1 over G. Because of that, if T sub C of Z does not have the same pole zero relationship, you're going to have poles at infinity in C of Z. Meaning, just take a hypothetical, and maybe I do that here, but let's just say, given this formula, the pole zero excess in G of Z, let's say it's 2. Then if we don't have the same pole zero excess in the ideal plant that we're trying to end up with of 2 or greater, then we're going to have poles at infinity in our controller, C of Z. So here is a long-winded, that's why I wrote it before class, but you can go home and read this and sleep on it and study it, but hopefully it will start to make sense at some point. The restriction on the pole zero excess in your original, in T sub C of Z makes sense. In your ideal, that's what we're trying to fit or make happen by the choice of our controller C of Z. So here, suppose G of Z has a pole zero excess of 1. That means maybe if your denominator was third order, what's your numerator order in your plant, G of Z? This isn't hard, but just kind of keeping track. So you have a second order numerator and a third order denominator. You have a pole zero excess of 1. That's what G of Z looks like. That's what you've found from your model, from your zero order hold equivalent. G sub C of Z has a pole zero excess of 1. One more pole than 0. If you think about that, if you now multiply everything through, try to picture what's happening with the input-output relationship in that system that has a pole zero excess of 1. Now you have a 1 sample period delay between your reference input and your output. So if you kick the system, you're not going to see anything happen from that kick until 1 time step later. That's what I mean by a 1 sample period delay. So you kick your system now. If there's a 1 sample period delay, nothing's going to happen for the until the next sample period. You're not going to see it when you hit it. There's going to be a 1 sample period delay with a pole zero excess of 1. Forcing your desired or ideal closed loop transfer function, that's what we're calling capital T sub C of Z, to have that same pole zero excess or more pole zero excess. That means that if you kick that guy, he's not going to respond instantly either. He's going to respond the same way or slower than your original plant. That's what that means. By forcing your ideal transfer function, T sub C of Z, to have the same or more pole zero excess than your original plant. So that's restriction number 1. Questions on that? I know that's maybe kind of weird, but just think of kicking a system, and then if you have a 2 sample, or if you have a pole zero excess of 2, you have to wait 2 sample periods before you see anything coming out at the output. So you can't force your ideal transfer function to behave faster than that. That's what this is saying. You can't say, oh, my original system had a pole zero excess of 2. I'm going to make my plant instantly respond. Well, that's going to force your controller to be non-causal. It's going to know what's happening before it even happens. And that can't happen. Not in a controls class. Okay? You can't go, ow! Right? You maybe didn't catch that on the audio at home, but somebody caught it. Are there questions on restriction 1? Here it is. That's the causality constraint. That's another way that we will refer to restriction 1, the causality constraint. You can't make that T sub C of Z respond sooner or faster than your original plant. And that means that your controller has to be causal. It can't be non-causal, your controller. It can't predict the future or anticipate the future. Although when we start talking about PID controllers with that derivative action, it's anticipating what's going to happen in the future. Just as a heads up. That's a side, I should have said sidebar, but don't worry about that right now. That's restriction number 1. We have 3 more restrictions. The next 2 hinge on the need to keep our system, our closed loop system, internally stable. And hopefully you remember that that starts to then say, oh, we need to worry about these other 3 transfer functions. The transfer function from the reference input to the air, from the disturbance to the output, and from the reference to the input. Those 3 transfer functions have to be bounded input, bounded output stable, in addition to T sub C of Z being stable. So the next 2 restrictions, R2 and R3, are to guarantee internal stability, which we said one way to ensure internal stability was to not have our controller canceling unstable poles and zeros in the original system. Here's restriction 2. R2 says that unstable zeros in our system, in our original system, G of Z, we need to keep those factors in our T sub C of Z. Unstable zeros in our plant must be present Oh, I forgot my spell checker's not working in this. Every time I spell zeros, I think you can do it either way, but if I type it Z-E-R-O-S, it underlines it in Word. So I'll include the E here for the plural of zeros. Unstable zeros in G of Z must be present as zeros in T sub C of Z. That means when you're building up T sub C of Z, if you have unstable zero factors in G of Z, you better initially just put those into T sub C of Z. And you have to just live with that. That's pretty easy. You just put them in there for T sub C of Z. And remember that you're going to have to maybe introduce more poles because you need the pole zero excess to be the same in T sub C of Z as in your plant G of Z. That's restriction 1. Restriction 3 is unstable poles in G of Z must be made zeros Let me not say in, but of that 1 minus T sub C of Z expression. Meaning you now will evaluate this expression at the unstable pole location and say that quantity has to equal 0. That's what I'm meaning here. And that's going to force certain restrictions or relationships on unknown coefficients in T sub C of Z. Those are restrictions 2 and 3. The last restriction is the result of steady state accuracy. Tracking error, making that error small due to a constant, due to a ramp, due to a parabolic input. Steady state accuracy then leads to restriction 4, again on T sub c of z, and that says that steady state accuracy, what's the steady state error, for example? Steady state accuracy may impose additional constraints on your desired transfer function T sub c of z, and maybe relationships on T sub c of z as z goes to 1. Let's just look at what I might mean by that before we get into a full-blown example. Let's say example of R4, restriction 4. That's dealing with steady state accuracy, and anytime we're dealing with steady state accuracy, wow, where is it? We're worried about what this error signal is doing. If our system is performing properly, we might like this output Y to be tracking R, our reference input. And so we have certain conditions we want E, our error signal, to satisfy. That's our steady state accuracy. Here's an example. The error is just created by comparing the reference input R to the output Y. We're assuming unity output feedback. The error signal is just R minus Y. But we know how Y is related to R. Y and R are related by the ideal transfer function. So we could rewrite this as R of z minus T sub c of z, R of z. That's just Y of z. Well, that means that we have 1 minus T sub c of z times R of z, giving us our error signal, E of z. Suppose we said, oh, what if our input, R, is a step? Let's just say it's a unit step even, a constant. And we want our output to track that step without any error. So we say, here's a 1, and we want our system to follow that 1. So we want it to lock on to 1 and be 1. The output, we want it to be 1 after the transients have disappeared. If we want zero error due to a constant input, what's the z transform of a constant? What's capital R of z in terms of ratio of polynomials of z? Do you remember? Oh, come on. Spring break was that long? Z over z minus 1. And now we can actually apply the final value theorem, because we want to know what's the error as time goes off to infinity. Well, we can find that value from our final value theorem by looking at a limiting condition on capital E of z as z goes to 1, as z goes to its DC location. if we want zero air, and here is our formula for the air, 1 minus T sub C quantity times R of Z, we can now find that, and sometimes I'll denote this as E sub infinity, and that's the time domain signal of our air coming out of that summing junction after a long time. And what's infinity? This is where we can kind of play fast and loose with our wording. What is infinity when we're talking a control question? How far into the future? To infinity and beyond. After we've settled, right? So our settling time, if we're beyond our settling time, that is effectively infinity. So now all we have to worry about is, oh, sometime a little bit after our settling time, and we're at infinity. And what is that? Well, in an analog control setting or in a continuous time, you're saying e to the minus 5 is 1%. It's actually 0.006, so it's less than that. But we're getting close to 0, e to the minus 5 time constants. So if you know your dominant time constant, 5 of those, and you're at infinity. So if your time constant, and in electrical engineering, your time constant's usually pretty fast, but let's say we have some mechanical, electromechanical system, and your time constant is half a second. 5 of those, 2.5 seconds later, and we're at infinity. To infinity and beyond, 3 seconds, and we're at infinity. That's what this little e is. So maybe 3 seconds into our process of changing the set point, setting our reference to a step, we want the output to be locked on to the input. And that makes sense. I mean, if you're flying an airplane and you change something, maybe you want to be tracking that within a reasonable amount of time. You don't want to wait for infinity before that happens. Or, you'll really get dirty looks from the airline when you say, oh, when are you going to reach the destination? Oh, in infinity. You may not get very many ticket buyers with that. So now this is the limit as n marches off to infinity of e of n. So we are taking this all the way to infinity effectively, but we know that's not very far into the future, actually. By the final value theorem, that's the limit as z goes to 1 of z minus 1 e of z. Here's where we're invoking the final value theorem, is that equality. Now let's see what that right-hand side does. Well, that says then that we're looking at the limit as z goes to 1 of z minus 1, but e of z, remember, was 1 minus t sub c of z times r of z, but r of z was a unit step, and that's z over z minus 1. Which now we can cancel that. As z goes to 1, what happens to this rightmost term in the numerator? That's nice or well-behaved, isn't it? That's going to basically be gone. And now we're looking at, as z goes off to 1, we're looking at 1 minus t sub c evaluated at 1. Oh, evaluating that at dc, remember? And what do we want? We want our air to equal 0. Meaning, if we are wanting zero air due to a constant input, we need to force t sub c of z to have a dc gain of 1. So if there's some unknown coefficients in t sub c of z, this restriction 4 says, oh, we need t sub c of 1 to equal 1 from restriction 4. All right, so let's now walk through an example of this process. Direct design method of Ragazzini. Almost makes me want to get hungry, right? Ragazzini. What are we having for dinner? Never mind. Example. Suppose somebody gives you a hypothetical plant for z minus 1.5 over z minus 1/2 z minus 2. And now you can maybe understand why I put this horizontal dash on my z's. If I didn't, my 2's and z's would get confused. That's why I always use script s's, because my s's and 5's would look the same. So somebody might say, why are you writing a script s when you do Laplace? Believe me, you're happy that I'm doing that so that you don't confuse an s with a 5. Same with the z's and the 2's. What can you tell me about this plant? Anything? If somebody was in an interview, interviewing you, and they said, oh, you've had digital control. Here's a plant, g of z. Tell me about it. Oh, you had THARP for control, didn't you? Is the interview over? So what are you going to do? What can you tell the interviewer about this plant to show that you have a little bit of a connection, a little bit of insight into what's going on here? It's unstable, isn't it? In the open loop. If you just kick this guy, he's going to go unbounded, isn't it? So one is you have a system that's unstable. All right, so let's just start keeping track of these, because these things that you're seeing are influencing what t sub c of z is going to be, how we're going to create that. Observations with g of z. One, you just told me that g of z was unstable, and if you really want to impress your interviewer, you might say, oh, g of z has an unstable pole at, and if you don't know, don't say this, just say, oh, it's unstable. So I was, never mind, but I have an audit coming up, and no, it's a review, not an audit, so on space. I said outer space? No. Okay, so back to reality, not outer space. Where's your unstable pole? It's outside the unit circle. And it's in the denominator, right? Poles are downstairs. So you have an unstable pole, and it's at 2. You have a stable pole. Does that mean you're halfway stable? No. You could have 100 stable poles and 1 unstable pole, and you've got problems. It only takes 1, right? 1 apple, is that right? 1 bad apple spoils the whole bushel. I don't know. Food theme tonight, I guess. Can you tell me anything more about g of z? Is there anything else interesting about g of z besides it being unstable? has a pole zero excess of 1, doesn't it? Because we're going to need that from restriction 1, aren't we? So G of Z, so we're maybe not thinking of these in restriction 1 through in restriction 4 order, but at least you're coming up with the right ones. G of Z has a pole zero excess of 1. What in the world has a pole zero of 1? Man, I'm still thinking about that rotten apple. G of Z has a pole zero excess of 1. Anything else? Remember your restrictions. R1 was concerned with causality or the pole zero excess. Okay, you've talked about that. Restriction 3 was dealing with unstable poles of G of Z. Okay, we have one of those. 2, what was restriction 2? Unstable zeros. Do we have any of those? Yes, we have a zero factor outside the unit circle, and those make problems. Unstable zeros make your system more challenging to work with. A bicycle has an unstable zero. Duh. So that means that if you want to go right, you actually kind of go left before you go right in with unstable zeros. You sort of go counter to where you want to end up. That's the behavior of unstable zeros, or one property of unstable. They make your design problem more challenging. So anytime you have an unstable zero, you go, oh no, this is going to make it a little bit more, you can't just really hit your system hard. By that I mean you can't really crank up the gain necessarily with an unstable zero. Things could go haywire. So that puts a little bit of a twist on your options. So that's observation number 3, is that G of Z has a zero outside the unit circle. G of Z has an unstable zero, and where is that at? At 1.5. At Z equal to 1.5. Yes? Pardon? Okay, the question is, why do we need this zero stable? You don't have a choice. Depending on your system, it's just going to appear either inside the unit circle or outside the unit circle. It's easier for your control problem to have stable zeros. That's all I'm really going to say now. It makes your job of controlling the system more challenging or more difficult when your zeros are outside the unit circle. You don't need zeros inside the unit circle, but it's nice to have them inside the unit circle. Is that distinction clear? So you don't need zeros inside the unit circle, but it would be nice if they started there, but a lot of times you don't have a choice. You might build a system that has an unstable zero intentionally to give yourself, like they've made fighter aircraft unstable by design, but that gives them more maneuverability. No, the unstable zero doesn't really make it unstable. It doesn't make your system unstable. It's just in the region of where you would call your poles unstable, so we refer to it as an unstable zero. It's just outside the unit circle, and instead of saying you have a zero outside the unit circle, it's just convention to say you have an unstable zero. So it doesn't, that's good. That was a good comment. It doesn't make your system unstable, but it makes your job of stabilizing, if your system is unstable with poles, it makes your job more difficult. And even if you have a stable system, open loop and unstable zeros, it makes your control problem more challenging. But it doesn't make your system initially unstable. Maybe that was your question. Thank you. Other questions on that? We've made 3 observations, and now the interviewer is impressed, right? Wow, okay. Who did you have for control? Tharp, really? Now, what do we do with that? Now we need to figure out how to build our desired controller, transfer function. So now let's look at this design of T sub c of z. And maybe if we need to, we'll say that's a ratio of 2 polynomials, a numerator polynomial for t, so I'm going to subscript it t, and a denominator polynomial of t sub c, so I'll just subscript that polynomial as d sub t of z if I need to. But this is what we hope to accomplish by the controlled system. This is our desired, and I know you're texting all of this, so CLTF, closed loop transfer function. For all of you that are texting now, you can just say, oh, CLTF. And it'll be clear to the recipient of your text message, right? Hopefully that doesn't have any bad connotation. I don't know. Who knows? All right. So now we are trying to design the numerator polynomial and the denominator polynomial. And can we say anything about those right now based on our observations of our plant g of z? What do we have to do? And now go back to your restrictions. And I'll point you right to the right one. I won't on the exam, but I will now. Can you help me on? No. But today I can. Do you know how to pick n or d? N sub t of z or d sub t of z? Or at least part of it. What's restriction 2 say? If you have an unstable zero, put that unstable zero factor as a piece of t sub c of z. So we know at least some of n sub t of z already. We know it has to have one factor, z minus 1.5. That was what was the unstable piece of our numerator in g of z. So let's now just let n sub t of z equal alpha z minus 1.5. Alpha z, I don't even know how big it is yet. Might be 4th order. I don't know. Let's wait and see. See if the interviewer helps you a little bit. Guide you through the process. So this is from restriction 2. R2 says that have t sub c of z retain the unstable zero from your original plan, g of z. So at least we have a start. Now, maybe somebody needs to tell us what they might like this. The prof has an unstable pole. Where was I? I got all tripped up there for a minute. We're trying to build t sub c of z, aren't we? And we've barely started. We kind of have half of an idea what the numerator looks like. We might want to know what the denominator looks like. And somebody might have to guide us. They might say, you know what, I want a percent overshoot of 35% or less. Maybe I need a settling time of so much. Or I need a peak time of something. That's going to give you some guidance as to what you want your denominator to look like. Right? We didn't say anything, did we? I just gave you a plant and said, tell me about it. So now it's up to you. Now's when you start earning your keep, right? Well, let's just do something interesting. Let's make this system have a deadbeat response. Do you remember what that meant? This was a good use of the word deadbeat, actually. Right? What? All the poles are at the origin. All right, so let's just write that down. Let's just suppose, because nobody told us any different. They didn't tell us anything about the transient behavior. So let's just make a choice. And for that reason, I'm going to say suppose. So this is a design choice. Later, you're going to go, how come you put all your poles at the origin? I just felt like it. You might feel like putting them at a certain radius at a certain angle. That's okay, as long as it makes sense for your particular problem. Let's just suppose for this is a classroom academic problem, isn't it? So suppose we place the poles of T sub C of Z at the origin. I just like saying that. So T sub C of Z is going to be a deadbeat response. So T sub C of Z will have a deadbeat response, which means if you apply a constant input, after a certain amount of sample periods, you're going to be constant. Your transients will all be gone. It won't take an infinite amount of time to reach your destination. It will reach it in a finite amount of steps. Do we need to worry about any of these other restrictions? What did we have about our plant, G of Z? Did we have anything that might apply from R3? Yeah, we had an unstable pole, didn't we? What's this tell us? This says we better force 1 minus T sub C of Z to have a 0 at that unstable pole location. That's what restriction 3 is saying. So from R3, restriction 3, that says that we need, and let me see if I can sort of make this wasn't our unstable pole at 2? So we take this expression, 1 minus T sub C of Z, and we force it to be 0 at that unstable pole's location. Well, we maybe haven't even picked all of T sub C, so let's just try something. Suppose we try, well, what do we need? We need to make sure that we're satisfying constraint 1 or restriction 1, which was associated with what? Pole 0 excess, wasn't it? So why don't we try, let's not go any bigger than we have to. We know that the numerator is that. Well, if we're not going any more than we have to, what if we just say that alpha of z, that remaining polynomial piece, is just a constant? Let's just say it's k. And then what do we know? All of our poles are going to be at the origin by the deadbeat response condition. How many poles do we need if we just need the bare minimum? I'm hearing a few different answers. How many do we need? You're missing this at home. You'll have to show up. Huh? How many do we need? 2, right? We need 2 poles because we need a pole zero excess of 1. We need at least 2. And if we want the smallest complexity of our system, let's just stick with 2. We could make it 3. Then our pole zero excess would be 2, which is bigger than 1, right? We need 1 or bigger for our pole zero excess because g of z had a pole zero excess of 1. Is that clear? So this can be z squared. Let's just try this and see if it works. 1, we know that this choice for t sub c of z has the correct pole zero excess. And now we have a structure for t sub c of z that we can substitute into this expression to try to satisfy R3. So our location of the unstable pole at z equal 2 will provide us or allow us to say, oh, 1 minus t sub c of 2, which t sub c of 2 is k, 2 minus 1.5, since that was z minus 1.5. Downstairs it was z, quantity squared, and z we're saying is 2. We want that to be equal to 0. Is it clear where that came from? That's restriction 3. We need that expression to be 0 so that we don't have our controller trying to cancel that unstable pole. That's the whole point of this restriction. Because we can't cancel unstable poles and zeros. Restriction 2 and 3 are based on that premise or that understanding. So now we just solve for the only unknown in this expression, which is k. So now we can see that k, whoops, I can't even do my algebra. Don't tell my 11th grade teacher. I was a slow starter. Just kidding. You know, that was back in the day, so I was well ahead of the other guys. No, teasing. Where were we? Oh, solving for k. So this is k equal what? 8. So now we have our t sub c, don't we? We have all of the pieces, and it seemed to be okay with what we needed. So now t sub c of z, this is what we're hoping to accomplish, is now 8 z minus 1.5 over z squared. That's the first design step. That took a while, didn't it? We had to use all of those different restrictions to come up with this t sub c of z. Now we can do step 2, which is to find capital C of z, or our controller. And what was our design formula? C of z was this 1 over g of z all times t sub c of z over 1 minus t sub c of z. This was our design equation. So now c of z is 1 over g of z. Now I forgot what g of z was, but that was 4 z minus 1 and a half over z minus 1 half z minus 2. That's 1 over g of z. And then we have this ratio of ratios. T of z was 8 z minus 1.5 over z squared, all over 1 minus that same expression. Let's figure out what this denominator in the denominator looks like. That's now, if we put it all over a common denominator of z squared, we now have z squared minus 8z plus 1 and a half times 8, which is 12. So that we can start cleaning this up a little bit. We can say, oh, that's what we wanted to have happen. We didn't want c of z to be canceling that unstable 0, so now we've basically eliminated that factor in our denominator of c of z. That's a good thing. We can also get rid of the common denominator in the numerator and denominator of that right-hand side expression. And we're left then with the denominator of the denominator becomes our numerator, so that c of z is now going to be z minus 1 half z minus 2. That's coming from the first piece. And, well, maybe I won't do it all in one step. So now, oh, I could have done that, couldn't I? I could cancel the 4 and the 8 and get down to a 2, so that I now have 2 over z squared, and I have z squared minus 8z plus 12 over z squared. I'm doing this in maybe a lot of detail so that you kind of see where this is coming from. And now let me factor that z squared. So now I have c of z is 2, z minus 1 half, z minus 2, z squared minus 8z plus 12. But that is z minus 2 times z minus 6, right? As a factored form, which is good because I better not be having my controller canceling that unstable pole at z equal 2. And if I had a numerator factor sitting up there, it's going to cancel it, that z minus 2. So in this process, I've now allowed that to be eliminated, and my controller now is going to be 2 times z minus 1 half all over z minus 6. Do you see anything sort of interesting here? An unstable pole. But our system was unstable, wasn't it? Here's where two wrongs make a right. We have an unstable plant, an unstable controller, and we end up with a stable system. Sometimes you have to have that. Sometimes an unstable plant cannot be stabilized unless you have an unstable controller. I mean, if you've got an unstable plant to begin with, might as well do as best you can or as much as you can to make the closed loop behave. And that may mean you have to have an unstable controller so that the combination ends up stabilizing the closed loop system. If we now apply this C of Z in the classical configuration by design, here is our C of Z, here is our G of Z, by design, we've now said that this closed loop combination effectively looks like T sub C of Z, which is 8 Z minus 1.5 over Z squared. And what influences stability in this closed loop system? The feedback has helped us, hasn't it? It's now stabilized. We put an unstable controller together with an unstable plant, fed that back, and we end up with a closed loop system behavior that's actually stable. And it even has a deadbeat response. Now I might say, what's that system behavior look like? Oh, I didn't have MATLAB. Couldn't tell you. Well, it's a deadbeat response, so that makes it a little easier. Now you can impress your interviewer. You can say, oh, you want that for your response? Or you may say, you know, let's see what we can get if we force a deadbeat response on this. Let's look at the time response that results from that closed loop system. We could simulate this with MATLAB, but it's more fun to actually do it on a napkin, especially in front of an interviewer. You can just pull out a marker and start doing this on a napkin. And I typically, when I'm teaching these control classes, I'm always talking about doing it on a napkin, and at the end of the semester one time I ended up receiving a napkin with some comments on it. It was a closed loop block diagram and some other remarks. It was a CLTF if you're texting along. So time response behavior of T sub C of Z. And we know if our analysis and our work is correct, we better end up with a deadbeat response, whatever that means. Let's see what that means. We know T sub C of Z, if we control that system, is this transfer function between the reference input R and the output Y. So it's Y over R is 8 Z minus 1.5 over Z squared. But this is one of the nice things about being able to stabilize unstable systems, is maybe I won't fall down, is that you don't have to solve differential equations. You can just play with difference equations. So if I now want to put this into something that relates Y and Z, why don't I not play in Z's, but Z inverses? Let me multiply by an effective 1, which is, let's say, Z to the minus 2. Since my highest power of Z is Z squared, let me get rid of that. Meaning, let me now multiply this guy that way, so that this now becomes 8 Z to the minus 1 minus 1, well, let me multiply that 8 through, minus 12 Z to the minus 2 over 1. And that again is relating Y to R. So that now I know if I cross multiply, I have y of z times 1 is equal to 8z to the minus 1 minus 12z to the minus 2 times r of z. That's in the frequency domain, but we can put that very quickly into the time domain in order to get a difference equation. And difference equations, all we have to do is kind of recursively number crunch, and we can get an answer. What's this look like in the time domain? This relationship between our reference input r and our output y. What's capital Y of z in the time domain? We're inverse Z transforming. Y of n. It couldn't get easier, could it? Capital Y of z is just y of n. The next piece is 8 z to the minus 1 r of z. What's that in the time domain? I'll do the hard part. There's our governing relationship, difference equation. It's no longer a differential equation. We're in discrete time. This is our linear difference equation relationship between our reference input and our output y. And what if we apply a constant? What if we say our reference is 1, a step? Let's see what y does. Right? If you kick it, we're interested in how it responds. And you know, I hope, that it's going to behave like a deadbeat response. So let's let our input be a unit step. Which really just says r of n is equal to 1 for all n greater than or equal to 0. That's a unit step. What's y of 0? Well, we can just plug in the right-hand side. That has to be 8 times r of n, which is 0 minus 1, so that's r of minus 1, minus 12 r of 0 minus 2. And what are r of minus 1 and r of minus 2? They haven't turned on yet, have they? So y of 0 is 0. We kick this with a 1 at 0, and what do we get out right then at the output? 0. Does that make sense based on your pole 0 excess? Your pole 0 excess was 1, wasn't it? So you better not see any response immediately when you hit it. The first time you should maybe see something is the next time, at y at time n equal 1. And now we can find that one, because we have, well, the deadbeat response basically says your output y is just a linear combination of previous inputs. There's no output there. You don't have to worry about the memory in our system, so to speak. What's y of 1? Y of 1 is now 8 r of 0 minus 12 r of minus 1. That's just 8, isn't it? What's y of 2? Eight r of 1 minus 12 r 2 less than n, 0. This is now 8 minus 12 or minus 4. So we started at 0. At 0 we hit this with 1, and we just keep pushing it with 1. And what happens to y? Initially nothing. Then it jumps up to 8. The next time step at 2, it jumps back to minus 4. What's going to happen at 3? Do you see what's happening? Y of 3 is 8 R of 2 minus 12 R of 1. But R of 2 and R of 1, R of 3, R of 2, they all look the same, don't they? This is again going to be minus 4. So that what do we have? We now can sketch our response. Here's time. And we didn't need MATLAB, did we? We did this all on a napkin. This is now y of n. One, two, 3, 4. At 0, whoops. Oh, I knew that was going to happen. That's what happens when you have a smart tablet. It gets a little too smart, because I don't usually make mistakes, so I'm not going to be going like this. That's why I usually work on paper or on napkins, right? It doesn't try to correct for my mistakes automatically. I can just mark them out. There's where we were at 0 up to the first sample period. Then what happens? Y of 1, we jump up to 8. Then what happens? Then we get down to minus 4, don't we? And we just keep there. Do you see the deadbeat behavior in this response? How many times did it take us before we got to a constant? 2 after sort of a 1-period delay, right? So a transient act was really sort of too long, TWO long, not TOO long. And it stopped changing, didn't it? We didn't change the R, and so we stopped changing in 2 sample periods. Is this an acceptable response? You'll have to decide. But what did we do? We hit this system with a 1. But initially, what was our system behavior going to do? What was G of Z? Remember you told me? It was unstable. So it was just going to go unbounded if we didn't do anything. At least this is a bounded response. Maybe it's not acceptable. Maybe we might want to do something else, but we can now at least stabilize the system. And we did it with, what? The design method via Ragazzini. So this gave us a way to start. Maybe this isn't how we want to always be designing our controllers, but it does give us this deadbeat response, and it does stabilize the system. Questions on that? Yes? No? I wanted to get through another design, which was a DC motor design, and I only have about 14 pages to go. I have a pole in the outside the unit circle, don't I? Well, you saw that already earlier, right, with the trip. But I may do this offline. I may do that example offline, and you can watch it. You were asking if things are available offline, but you can then not have to pay for your sleeping pills. You can just watch a YouTube video. I'll see you Monday.